So this is going to be the end of chapter 18. And then if you'll notice on the syllabus, we're skipping chapter 19. I honestly cannot remember what chapter 19 is right now, but I think it's nuclear chemistry. But we're skipping it and we're going to chapter 20. I hate that I can't remember it now, but I don't have my textbook at home. So there's not a mistake. You're not going to be missing anything significantly important on the TEKS. It's just going to, the information in there is not as important as what we're going to move on to in chapter 20. So we said earlier that 70% of the earth is covered with seawater, has an average depth of 3,800 meters. And so you may remember Sheridan said at one point that it's crazy that we know more about outer space than we do about what's under the sea. And that's because it's very deep. We can't actually explore most of it, so there's a lot that's still unknown. So only 30% of Earth is considered dry land, and it's where we all live. Most of the ocean, like we said, is still unexplored. So the ocean is one continuous body of salt water that covers Earth's surface. But there are what we call three principal regions. And so even though we think of them as individual oceans, they are all interconnected at some way, some point. The three principal regions are the Atlantic Ocean, which is on our east coast, on the west coast of Africa and Europe. It's the second in size. The Pacific Ocean, which is on our west coast and is on the eastern coast of Asia, Japan, Australia, and it's the largest with the greatest depth, the deepest ocean. The Indian Ocean is between the eastern coast of Africa, south of India, and the western part of Australia, and it is the smallest surface area, and that's our third principal region. Now, a sea is going to be a smaller region of salt seawater that's distinguished by unique special characteristics. So you have the Mediterranean, which is going to be on the northern part of Africa, south of Italy, in that area, east of Spain. And then we're going to have the Gulf of Mexico, which is obviously should be known to us. It's in the little hook of the United States that Florida and southern part of I think that's Mexico, create. And then you have the Caribbean Seas, which is over islands like Cozumel. Well, actually, that's in Mexico. Let's see. Why is it escaping me? I'm thinking of Haiti. And that's the only one I can think of. Caribbean islands. Let's see. Cuba, Puerto Rico. It's going to be above South America. So like Nicaragua, Guatemala, Venezuela. So it's kind of a smaller region. Oops, sorry. So the nature of seawater, there's going to be, it's associated with a level of salinity, which is the amount of salt dissolved per kilogram of seawater. On average, it's 3.5%, but there are variations that occur, meaning there's areas of low salinity and areas of high salinity. When we have a lot of precipitation in a certain area, it's going to dilute the salt water, which basically decreases the salinity. Other things that do that is ice melting and river inflow. So in areas like New Orleans, where the Mississippi River is merging with the Gulf of Mexico, the saltwater there actually is not as high in salts as it would be if you went further out away from that freshwater source. But the proportion of ions is relatively constant, meaning if I was to take a sample, I would have relatively the same proportion, ratio 1 to 1, 1 to 2 of ions, no matter what. Now in the saltwater, we also have important dissolved gases, nitrogen, oxygen, carbon dioxide. Those are important for the things that live under the ocean, the underwater plants, the fish, aquatic life, the corals that live out in the sea. And so you do need to know, this is an important slide to know. So the things that are dissolved in water in the major components, sodium and chloride, which are table salt, NaCl, are the two major ones. Everything else is pretty much less. If you see, sodium and chloride make up about 85%. And so everything else, the sulfate, magnesium, calcium, potassium, bicarbonate, bromine, they all make up less than 15% of seawater. Now, movement of seawater, there's two main motions that we see, waves and currents. Now, waves are going to be produced by disturbances, just like sound waves and that we talked about before. We talked about wave motion produced by a periodic, it's a periodic motion produced by a disturbance. Currents are going to be movements of water from one place to another. So this is what's going to transport material, or our currents, whereas waves do not transport energy, do not transport material. So waves, just as a reminder, we have moving crests and troughs, and you can see a picture of a wave here. There's three characteristics: the height of the wave, which we called the amplitude. It's from the trough to the crest. We have the wavelength, which is the same as the distance between two crests, two troughs. And this one's going to be between two successive crests, so two waves. And then we have the wave period, which is the amount of time it takes for the crest to pass by. So once the first wave comes in, we start timing it, and when the second wave comes in, we stop timing it, and that's what we call the wave period. So very similar to our wave discussion before. Now, swells are going to be things that carry energy but do not transport water. So the individual particle motions are circular. So if you see here beneath the wave, there's no movement below the depth of 1/2 length. But as we go up, you start to see this circular motion, right? And so that is called a swell, where you see this individual circular motion. Now, when we have a very strong swell, we're going to have whitecaps, and they're formed when the top of the swell is toppled by a strong wind. And so we've seen whitecaps if you've been to the beach on a very windy day, or seen a movie or a TV show where they're surfing and they're trying to surf, and you'll see those waves will kind of fall and spill over, and that creates that white look, the foamy look of the ocean, which is called a whitecap. So shore effects. I was just trying to move this slide. So if we have these waves coming into the ocean, or to the beach, you can see they have the swells, the circular motion there at the bottom, the crests, the troughs, and then as you get in, you have this surf zone and a breaker. Okay, so the breaker is at depths less than the wave height, lower, and the lower part starts to slow down, and the top part breaks forward. So what that means is, it's kind of like, have you ever seen those funny videos where somebody's walking and all of a sudden their like feet start moving slower than their head, and they start walking with their head forward, and then they fall because they're not balanced and their head is going down first. Well, that's what the waves are doing. The bottom of the wave is slowing down, but the top part isn't slowing down at the same rate. It's going to topple over. And so that's what the breaker is that wave toppling over. Now, the surf is the breaker formation zone. So you can see here on this picture, all of these waves coming in. These are going to be where you have the breakers occurring. And that's where people are going to want to go out and surf. They're going to go out and get behind it, and then they're going to try to ride in on one of these breakers as it's coming into shore. I have never been surfing, so I don't know that, but everything I've seen based on TV and movies tells me that that's what's happening. All right, so some other shore effects. Water transported towards shore by the breakers has to be returned, right? Water doesn't just keep coming in. It's going to have to be returned. So there's two ways that this occurs. The first is called an undertow, and the second is called a longshore current. So the undertow is what takes you out into the ocean. So it's the direct return of water under the breakers, and so it's underneath where the water's toppling over. But it's what happens if you've ever been to the beach or seen a movie about the beach or anything like that, where if you're out in the ocean and you're playing, and next thing you look up and you're like, holy cow, how'd we get all the way out here? Well, it's pouring outside. It's okay. It's just pouring. My son does not like weather. Hey, quit. Calm down. but you're like, how did I get all the way out here? Well, you've been caught up in the undertow, but you don't really feel it, and that's what takes you out to shore. It's a very dangerous thing for people who aren't very strong swimmers, but it happens kind of very subtly, but it's underneath, and if if it's not a very strong feeling, you may not even notice it. So the longshore currents are motion that's parallel to the shore, so it's a little bit different, but the way it works is if you were to set up like your camp at the beach and you walk straight up from your camp and you go out and you get into the ocean and you play, and next thing you know, you look up and you have moved like 50 feet down shore from your camp. Hey, you're knocking dirt and stuff off the fan. Please quit, okay? It's okay. Please, can you go into your room and just give me 10 more minutes, okay? Please. I'm asking nicely. If you think you want to be an elementary school teacher, you can come to my house and practice. Go. So then this is called the longshore current. So you're being moved down the shore, but you're not being moved out away from the shore. It's just moving along the shore. And so then once you get out, you have to walk back to your camp where you've set everything up because you've been moved down along the shore side. Okay. All right, the rip current is going to be a strong stream of water pushing out against the wave. It usually extends beyond the surf zone and then diminishes. So when we have a strong rip current, the things you're going to see is you're going to have a lack of surf. So these are like the not good surfing days. There's not a lot of whitecaps, not a lot of breakers. The water might be darker, deeper channel, instead of being light and lots of motion and movement, but there also might be a turbid streak of water. Okay, so turbid usually means like flow, movement, and so you can see here that the rip current would essentially just drag you out into the ocean. So when there's a strong rip current, usually there's warning signs telling you, I don't know if they call it like a flag warning, but it's a day where it's not necessarily to go out into the ocean unless you're a very, very strong swimmer, because you have the presence of this rip current, which is very strong and very difficult to overcome. And the way to get out of the rip current is to swim, not to try to swim back to the shore, but to try to swim horizontally to get out of the rip current. So if you can swim to your left or to your right and you can get out of the rip current, then you can come back to shore, versus if you are trying to swim. My cat's eating the fuzz falling off the fan. Oh my gosh. Things are going very well, guys. But if instead of trying to turn around and swim back to shore where you wouldn't be able to overcome the rip current. All right, so ocean currents. We kind of talked about these when I referenced Finding Nemo and the East Australian Current. So these are going to be streams that are within the ocean that transport water over large oceanic distances along roughly the same path. So they change a little bit seasonally, like fall and summer, but typically they are consistent. Now, these ocean currents, like the East Australian Current, are produced by two effects. One is the density difference in seawater, and so we'll talk about that on the next slide. And the other one are the winds blowing persistently in the same direction. So that's the wind happening right above the surface of the water. So in this image right here, you can see this is Iceland, Greenland, Antarctic. So this is eastern coast of Canada, up north, like north of Maine, up in that area. And you look on top, you have cold, dense Arctic water coming from the North Pole, and then you have Antarctic water. And you can see that the cold water is going to sink down, and it's going to force the warmer water up, where it's going to cool off, and then it's going to sink down, and it makes this kind of convective process. And so this is one of the things that produces it. It's a density current. So if you were to get down deep along it, you can see where it's going to turn into like a current. Now, the other ones are surface currents. So global circulation patterns that are maintained basically because of the patterns of prevailing winds, meaning the winds are always blowing in the same direction. Not your local winds, not the ones occurring today, tomorrow, wherever you are, but the big scale global winds, which are influenced by the rotation of the ocean and which influence the currents, which are also then influenced by rotation of Earth and the shape of ocean basins. So if we look here, you can see, I don't even think, you can see the current. But anyways, so looking along of North America, we have the Gulf Stream, which goes along Florida up along the East Coast. So unfortunately, this is where we find that a lot of our hurricanes well, I shouldn't say unfortunately, but they do typically swing out along that Gulf Stream area. But all of these arrows represent an ocean current, okay, that we can see. So you have the west wind drifts, the Falkland Current, Brazil Current, we have the North Pacific Current, California, and so these are all going to be examples of currents that we know of. Now, gears are going to be great systems of water circulation centered in mid-latitudes. And the direction is dictated by the Coriolis effect, which I just remembered I need to post that video because I did not. So I'm going to make a note right now that I'll post a YouTube video with the Coriolis effect. And these are going to be the ones that are, if you look on the southern hemisphere, you can see that there's several like counterclockwise rotations. And then if you look in the northern, you can see that especially the Gulf Stream up to the I think that's called the Canaan Current. They're more likely to be clockwise. Okay, so that has something to do with the Coriolis effect. So northern hemisphere, they tend to be clockwise. Southern hemisphere, they tend to be counterclockwise. Okay, so here is the global ocean circulation. Okay, so this is where essentially they're like a great train. If you've ever tried to ride the Dart in Dallas, it's very overwhelming, but it's very similar. You can travel through all these places in kind of one loop, and there's some stops and some connections, but it's very similar. So you have the current coming along from the eastern side. You can see the red means warmer, and the blue would be colder. So deeper currents. The purple is kind of like mid-level. But the red is closer to being like surface, warmer surface, and then as it goes purple, it's getting cooler, and then once it's blue, it's the deep, deep currents. Okay, so you can see they intersect and overlap, very similar to a like a highway system. So the ocean floor, the thing that we don't know much about. We do know some structural features. You need to know this figure. I'm going to try really hard between now and the next test to work on developing some of my own figures to then put into the test. I did not have that kind of time to devote to learning to do all of this stuff and write the test to keep us on track. But I am planning to put more figures in the next test, okay? So know this figure, and I think that's the second figure I've told y'all to know. So continental shelf, this is the part that we really know the most about. It's where our beaches are. They are the eroded continental margins, relatively shallow water, and so it's going to be this very shallow area. It's normally about, I think that's about about 0.2 of a kilometer deep, so very shallow. After you leave the continental shelf, it drops off very drastically to the continental slope. It's a steeper drop, a transition feature beyond the continental shelf, and it's often cut by submarine canyons, so like canyons really deep, not cannons like guns, but canyons like the Grand Canyon. Now this is the area where we start to know not a lot about. Most of our life is going to occur along the continental shelf, but the majority of the ocean is held within the continental slope. So then we're going to have this area called the Oceanic Basin, which is the deepest part of the ocean. It's characterized by practically level abyssal plains, which is a perfect name. It's if you've ever heard like Into the Abyss, I heard this great speaker one time. She was talking about her job and how one day she woke up and she realized that she was staring into the abyss and the abyss was staring back at her. And so then she decided to change her life and pursue a career that she was passionate about. And I think about that when I think about the abyss, because it's something we really don't know a lot about. But the reality is there's probably a lot of stuff going on down in that abyssal plain. But there's huge mountainous ridges, just like we have mountains on the surface of the earth. There are mountains underneath. There are trenches that are very deep that occur along the ocean basins. And we know that volcanic islands originate from these deep, low areas and produce things like the Hawaiian Islands, the Aleutian Islands that we see on the surface, but actually originate very deeply down and connected down into the ocean surface. Okay, so you need to make sure, feel comfortable being able to label or identify labels on this image. It might be something like matching, where you don't see the words, but there's letters there, and then there's drop-down options. Not quite sure, but I like the idea, and I think making a matching question is very possible for this here right now. Okay? All right, well, this ends your chapter 18. I'm going to start working on chapter 20 and try to get chapter 20 online soon. And please contact me, any questions, concerns, anything I can help with during this time where we're apart and doing online instruction.